My name is Kate Grier, and I'm a graduate student at The Ohio State University. Today I am here to discuss a recent paper entitled Stellar Velocity Dispersion Measurements in High-Luminosity Quasar Hosts and Implications for the AGN Black Hole Mass Scale. In this work, we present stellar velocity dispersion measurements in 4 high-luminosity quasars. We also rederive the virial F-vector used to calibrate black hole masses in active galactic nuclei using updated virial products. We then use this to re-examine the M-sigma relation. Over the past couple of decades, both observational and analytical work have suggested a physical connection between the growth of galaxies and the growth of their central black holes. The M-sigma relation, which is the correlation between the black hole mass and the bold stellar velocity dispersion of the host galaxy, is one of several correlations that has been observed between galaxies and their black holes. Among its many other uses, the M-sigma relation is important for black hole mass measurements in AGN, which are calculated using the virial equation shown. RBLR is the average radius of the emitting gas in the broadline region of the AGN, delta V is the velocity dispersion of the gas, and F is a dimensionless factor that accounts for the unknown geometry and orientation of the broadline region and may be different for each AGN. We are unable to directly observe the structure of the broadline region, so the true value of F for each object is unknown. Currently, a mean F factor is used, calculated by finding the value of F that places active galaxies closest to the quiescent M-sigma relation. Because of its wide use, it is important to have an accurate determination of the M-sigma relation. Velocity dispersion measurements in high-luminosity AGN are difficult to obtain because the AGN light often overpowers the light from their hosts. As such, there is a lack of objects at the high mass end of the relation. The success of an earlier program using the NIFS near-infrared integral field spectrograph and Altair adaptive optics system on the Gemini North telescope prompted us to undertake additional observations of quasars at the high mass end of the M-sigma relation. We observed 8 quasars with black hole masses that had previously been measured to be above 10 to the 8 solar masses. Using these data, we successfully measured stellar velocity dispersions in 4 objects. This figure shows the normalized ref frame spectra of these 4 objects, with the best fit stellar templates shown in red. The spectra of the other 4 objects we observed suffered badly from sky, telluric, and quasar contamination, and as such we were unable to obtain measurements for them. There are now 30 reverberation-mapped AGN with secure sigma measurements and virial products that were determined using traditional reverberation mapping methods. Recent success with a different reverberation method called SPEAR, discussed by Zhu et al. In 2011, prompted us to redetermine the time lags in virial products for this sample. We used SPEAR time lags for the H-beta emission line for the entire AGN M-sigma sample, either pulling the values from recent literature or using the actual SPEAR software itself when previous measurements were not available. We recalculated the virial products for the entire M-sigma sample. We then used our updated virial products and new velocity dispersion measurements to recalculate the mean virial factor F necessary to place active galaxies on the same M-sigma relation as quiescent galaxies. We obtain F equals 4.19 plus or minus 1.08. This is slightly lower than, but consistent with, most other studies. Here we show the AGN M-sigma relation with our updated virial products and new F factor. The AGN sample is shown in gray, and our objects with new sigma measurements are shown as black stars. The black and dotted lines show the quiescent M-sigma relation from Park et al. 2012, using the sample from McConnell et al. 2011. As you can see, all 4 of our objects fall within the expected scatter of the quiescent relation. To look for a possible morphological dependence in the relation, we also divided the sample by whether or not the galaxy is expected to host a pseudobulge or a classical bulge, as well as whether or not the galaxies host a bar. We see no evidence for an offset in galaxies with suspected pseudobulges or bars. If you'd like more details on this study, please take a look at our paper, which was posted on astro-ph today. Thank you for your time and have a great day.